Hello again, everyone. This is Sir Rick, and I would like to welcome you all to another video tutorial in our Math 10 class. Before we start, may I present to you our lesson objectives for this day. By the end of our meeting, you must be able to find the sum of terms of given finite or infinite geometric sequences. And second, you must be able to solve problems involving geometric series. So class, you already know what we mean by a geometric sequence. And our lesson last time is somehow related to our lesson for today, which is about geometric series. When we talk about a geometric series, we are actually just looking into the sum of the terms of a geometric sequence. Say for example, these are the terms of a finite geometric sequence. We have a sub 1 as the first term, a sub 1r as the second term, a sub 1r squared as the third term, a sub 1r cubed as the fourth term, until a sub 1r raised to n minus 1 as the last term of this geometric sequence. When I add the terms of this geometric sequence, I am actually forming a geometric series. Hence, a geometric series is a sub 1 plus a sub 1r plus a sub 1r squared plus a sub 1r cubed and so on until a sub 1 times r raised to n minus 1. Now, how do we get the sum of the terms of a geometric sequence? We actually have to just make use of the formula S sub n is equal to a sub 1 times 1 minus r raised to n all over 1 minus r, where a sub 1 is the first term, r is the common ratio, and n is the number of terms that we are adding. Let's try to look at our first example. Find the sum of the first 6 terms of the geometric sequence 3, -6, 12, and so on. So the problem, or from the problem I should say, we know that the first term is 3. Our common ratio is -2. That came from -6 all over 3 or 12 over -6. And the number of terms that we are adding is 6, or n is equal to 6. Now, since we are looking for the sum of the first 6 terms, then we are going to make use of the formula S sub n is equal to a sub 1 times 1 minus r raised to n all over 1 minus r. So plugging everything in our formula now, we have S sub 6, which is the sum of the first 6 terms of the geometric sequence, must be equal to 3 times 1 minus -2 raised to the 6th power all over 1 minus -2. Simplifying this will give us 3 times 1 minus 64 all over 3. Notice that 3 and 3 will cancel out, and what will be left is 1 minus 64. And 1 minus 64 will now give us an answer which is -63. Therefore, the sum of the first 6 terms of the geometric sequence 3, -6, 12, and so on is -63. So class, we can actually come up with an alternative formula to the formula S sub n is equal to a sub 1 times 1 minus r raised to n all over 1 minus r. Notice that this formula is used if and when the first term, the common ratio, and the number of terms are given. What if the first term, the common ratio, and the last terms are given? So we come up with the alternative formula for S sub n. Distributing a sub 1 in the numerator will give us S sub n is equal to a sub 1 minus a sub 1 r raised to n all over 1 minus r. Now notice that a sub 1 r raised to n is the same as a sub 1 r raised to n minus 1 times r. So that when you multiply r raised to n minus 1 and r, that still gives you r raised to n. So replacing a sub 1 r raised to n now with a sub 1 r raised to n minus 1 times r, we have s sub n is equal to a sub 1 minus a sub 1 r raised to n minus 1 times r all over 1 minus r. Now we know that a sub 1 r raised to n minus 1 is actually the last term of a geometric sequence. So replacing that with a sub n now, the last term of a geometric sequence, we have S sub n is equal to a sub 1 minus a sub n r all over 1 minus r. Now notice that this alternative formula is used if and when the first term, the last term, and the common ratio are given. Let's try to solve example number 2 using our alternative formula. Find the sum of a geometric sequence or the terms of a geometric sequence for which the first term is 125, the last term is 1/5, and the common ratio is also 1/5. Now notice class that in the problem, the first term is actually equal to 125, the last term is 1/5, and the common ratio is also 1/5. The number of terms is not given, hence we are going to make use of the formula a sub 1 minus a sub nr all over 1 minus r. Now, plugging everything in our formula, we now have 125 minus 1/5 times 1/5 all over 1 minus 1/5. Now, 125 minus 1 over 25 will give us actually 3,124 over 25, and 1 minus 1/5 in the denominator will give us 4 over 5. Simplifying this, we have 3,124 over 25 times the reciprocal of the denominator, which is 5 over 4. And that gives us 781 over 5. Now, simplifying or expressing 781 over 5 in mixed form will give us now the final answer. S sub n must be equal to 156 and 1/5. Let's try to look at our third example. A billionaire decided to celebrate Christmas as a Thanksgiving by donating 1 centavo on December 1, 2 centavos on December 2, 4 centavos on December 3, and so on through December 25 to the Lingap Kapwa charity. The donations form a geometric series. What is the total amount of donation? So since we know the first term to be 1, and I know that the number of terms is 25 because that's from December 1 to 25. And I also know that the common ratio is 2. Hence, we are going to employ or to make use of the formula S sub n is equal to a sub 1 times 1 minus r raised to n all over 1 minus r. So, replacing everything in our formula, or replacing the given in our formula, I should say, then we have S sub 25 is equal to 1 times 1 minus 2 raised to 25 over 1 minus 2. 1 minus 2 raised to 25 will give us negative 33,554,431 divided by negative 1. Or that gives me 33,554,431 centavos, which is the total donations. Now, converting 33,554,431 centavos to pesos will give me 335,544 pesos and 31 centavos. So the billionaire was able to donate this amount from on December 25 to the Lingap Kapwa charity. Okay, class. So since we're done with finite geometric series, we now move on to infinite geometric series. An infinite geometric series class is actually just the indicated sum of an infinite geometric sequence. So if the terms of an infinite geometric sequence are a sub 1, a sub 1r, a sub 1 r squared, and so on, then the infinite geometric series is denoted as S is equal to a sub 1 plus a sub 1 r plus a sub 1 r squared, and so on. Now notice, class, that there is no more subscript n in S because we do not know the number of terms of an infinite geometric series. Now, how do we get the terms of the sum of the terms, I should say, of an infinite geometric sequence? So we have the formula S is equal to a sub 1 all over 1 minus r. Now, notice, class, that a sub 1 here is the first term and r here is the common ratio. That there is a condition here that your r must be between -1 and 1, or in other words, the absolute value of our common ratio must be less than 1. Okay, class, let's try to make use of the formula in getting or in solving example number 4. Find the sum of the infinite geometric series if it exists, and then explain why the sum does not exist if, of course, it does not exist. So the series is 1 plus 1 over 5 plus 1 over 25, and so on. So from the given series, class, we know that the first term is equal to 1, the second term is 1/5. And so given the second and the first term, we can now solve for the common ratio. That's the ratio of a sub 2 all over a sub 1. That therefore gives us 1/5 divided by 1, which is actually equal to 1/5. So since, class, that the absolute value of the common ratio is less than 1, or the common ratio is between -1 and +1, then the series converges. In other words, the sum can be determined. So if the sum can be determined, we now are ready to look for its sum. S is equal to a sub 1 all over 1 minus r. So replacing a sub 1 with 1 and r with 1 over 5, that gives us 1 all over 1 minus 1/5, or that gives me 1 all over 4/5. And 1 over 4/5 is actually simplified as 5 over 4. Therefore, the sum of the infinite geometric series 1 plus 1/5 plus 1 over 25, and so on must be 5 over 4. Let's try our fifth example, class. Find the sum of the infinite geometric series if it exists, and then explain why the sum does not exist if it does not exist. The series is 4 plus 12 plus 36, and so on. Now, from the given series, class, we know that a sub 1 is equal to 4, a sub 2 is equal to 12, and the common ratio is equal to 3. That comes from 12 over 4. Now, notice, class, that the common ratio is actually greater than 1. Therefore, we cannot get the sum of the terms of this infinite geometric sequence. So we now say that since the absolute value of the common ratio is not less than 1, or the common ratio is not between -1 and 1, therefore the series diverges. And since it diverges, then we cannot determine its sum. Okay, class, so now let's try our last example. The first term of a geometric series is 3, the nth term is 48, and the sum of the terms is 93. Find the common ratio r and the number of terms n. From the problem, class, we know that a sub 1 is equal to 3, a sub n is equal to 48, and s sub n is equal to 93. Now, since we are looking for the common ratio r and the number of terms n, we are going to set up at least two equations also. So we now set up the first equation from the formula a sub n is equal to a sub 1 r raised to n minus 1. We know very well, class, that the last term or the nth term of a geometric sequence is defined by a sub n equals a sub 1 times r raised to n minus 1. So from here, we are going to generate our first equation. So we replace a sub 1 with 3 and a sub n with 48, giving us 48 is equal to 3 times r raised to n minus 1. Now, multiplying both sides of the equation by r will give me 48r is equal to 3r raised to the nth power. Okay, so where did r raised to the nth power come from? So that came from multiplying r raised to n minus 1 times r. Notice that if we have the same basis, we are multiplying exponential expressions with the same basis. We are just going to add their exponents. So n minus 1 plus 1 will give me n. So that leads us to our first equation, which is 48r is equal to 3 times r raised to the nth power. We also know that the sum of the terms is 93. So from that, we can generate another equation using the formula S sub n is equal to a sub 1 times 1 minus r raised to the nth power all over 1 minus r. So we replace S sub n with 93 and a sub 1 with 3, giving us 93 equals 3 times 1 minus r raised to the nth power all over 1 minus r. And cross multiplying 1 minus r with 93 will give us 93 times 1 minus r is equal to 3 times 1 minus r raised to the nth power. And distributing 93 on the left side and 3 on the other side will give me 93 minus 93r is equal to 3 minus 3r raised to the nth power. And since 3r raised to the nth power is the same as 48r, we can now replace 3r raised to the nth power with 48r, giving me 93 minus 93r is equal to 3 minus 48r. And combining all those with r's together on one side and the constants on the other side will give me negative 93r plus 48r is equal to 3 minus 93. Or that simplifies to negative 45r is equal to negative 90. And dividing both sides by negative 45 will give us now a value of r which is equal to 2. So the common ratio now is equal to 2. We also have to look for the number of terms because that's what the problem is requiring us. So from the equation 48 is equal to 3r raised to n minus 1, we should solve also for n. Okay? So replacing r from 48 equals 3r raised to n minus 1 with 2, we'll have 48 equals 3 times 2 raised to n minus 1. And dividing both sides by 3 will reduce this equation now to 16 is equal to 2 raised to n minus 1. Now we know very well that 16 can be expressed as an exponential expression to the base 2. And 16 is the same as 2 to the 4th power, and that must be equal to 2 raised to n minus 1. Now, since the two sides of the equation have the same basis, we are now ready to equate their exponents. So we now have 4 is equal to n minus 1, or solving for n now will give us a value of 5. Therefore, there are 5 terms in that particular geometric series. So our r is 2 and our n is 5. Okay, so before we end class, may I remind you to please try this activity on pages 10 to 11 of the second self-learning module that I have given you. Also, I would like to acknowledge the reference of this video tutorial. So that ends our video tutorial this day, class. I will see you again in the next video tutorial. Until then,